You think your internet comes from space, right? Like you send a tweet, it bounces off a satellite, and boom, someone in Tokyo sees it. That's what most people assume. Satellites, space, the future. Makes sense. Except it's completely wrong. Right now, as you're watching this, your internet isn't traveling through space at all. It's traveling through the bottom of the ocean, through cables, actual physical cables lying on the seafloor, thousands of feet below the surface, getting gnawed on by sharks. I'm not kidding about the sharks, by the way. We'll get to that. Here's what nobody tells you. 99% of all international data traffic, your Netflix shows, your Zoom calls, your Instagram scrolls, all of it travels through submarine cables at the bottom of the ocean. Not satellites, cables. And these aren't some backup system, they're the entire system. Without them, the internet as you know it just stops. In the next 15 minutes, you're going to understand how the actual internet works. Not the story we tell ourselves about satellites and the cloud. The real infrastructure. The physical engineering that keeps the world connected. And once you see it, you'll never think about sending a text message the same way again. So here's what's really happening. Every time you do anything online that crosses an international border, watching a YouTube video from Korea, video calling your friend in London, downloading literally anything from a server in Europe, that data is traveling through a cable lying on the ocean floor. Think about it this way. You're sitting in your apartment in Chicago, you pull up Netflix, you click on a show, that show is stored on a server in Ireland. Your brain assumes, okay, satellite beams it over. Wrong. That request goes from your laptop, through your Wi-Fi, through your internet provider's network, to a landing station on the East Coast, down into a cable that runs across the entire Atlantic Ocean floor, up to another landing station in Ireland, and then to the Netflix server. Then the data makes the exact same journey backwards. All of this happens in milliseconds. Through a cable, at the bottom of the ocean. Everyone tells you the internet lives in the cloud, but here's what they don't mention. The cloud is made of cables, actual, physical, tangible cables that you could theoretically go touch if you had a submarine and a death wish. And this matters because everything about how we think about the internet is backwards. We imagine it as this ethereal, wireless, floating thing. We use words like the cloud specifically because it makes us think of something intangible. But the internet is the most physical thing in the world. It's literally millions of miles of cable stretched across every ocean on the planet. When your Instagram goes down, it's not because the cloud evaporated, it's because some fishing trawler in the Atlantic accidentally snagged a cable with their anchor. When your Zoom call freezes, it might be because a shark bit through fiber-optic glass somewhere off the coast of Vietnam. This isn't science fiction. This is infrastructure, and nobody talks about it. Because the entire tech industry has spent decades convincing you that the internet is magic, that it just exists wirelessly, everywhere, all the time, but it doesn't. It exists in very specific places, and those places are at the bottom of the ocean. So let me show you what's actually down there. Because these cables aren't what you're picturing, picture a cable in your mind right now. You're probably thinking of something like your phone charger, right? Thin, flexible, kind of fragile, maybe as thick as your thumb. That's not what a submarine cable looks like. Not even close. A modern submarine cable is about as thick as a garden hose, sometimes thicker in shallow waters where it needs protection. And it's not just one thing, it's layers. Multiple layers of different materials, each one solving a specific engineering problem that comes with laying a cable across thousands of miles of ocean floor. Let's start from the inside and work our way out. At the very center, you've got fiber optic strands. These are thinner than a human hair. We're talking glass threads that carry light signals, and not just one or two. A single cable can have dozens of these fiber pairs, each one capable of transmitting terabits of data per second. Around those fibers, you've got a copper tube. This isn't for data, it's for power. Because here's something wild. Every 50 miles or so along these cables, there are repeaters. Little amplifier stations built into the cable itself. They boost the light signal so it can travel farther. And those repeaters need electricity, so the copper tube carries power to them constantly for decades. Then you've got layers of protection. steel wire for strength, polyethylene for waterproofing, sometimes Kevlar-like materials for abrasion resistance. In shallow waters near shore, where fishing boats and ship anchors are a threat, the cables get wrapped in even more steel armor. They can weigh over 100 pounds per foot in those sections. And all of this engineering masterpiece, just sits on the ocean floor for 20, 30 years, getting hit by earthquakes, getting gnawed on by marine life, dealing with pressure that would crush a human instantly. And it just works. But here's where it gets really interesting. How do you actually lay one of these things across an entire ocean? You can't just drop it like fishing line. The ocean floor isn't flat. It's got underwater mountains, trenches that go down 7 miles, volcanic ridges, shifting tectonic plates. You're trying to lay a perfectly functioning data cable across terrain that makes the Rockies look like a parking lot. And you're doing it blind, thousands of feet underwater with zero room for error. So here's how it actually works. And this part is genuinely insane. First, someone has to survey the entire route. We're talking months of ships dragging sonar equipment across the ocean, mapping every ridge, every trench, every underwater volcano. They're looking for the smoothest possible path. They're avoiding active earthquake zones where possible. They're steering clear of shipping lanes, fishing grounds, protected coral reefs, underwater volcanoes. They're planning a route that might be 7,000 miles long, accounting for curves and detours, making sure the cable won't end up draped over an underwater cliff or sitting in a volcanic vent. This planning process alone can take years. Then you need a ship. Not just any ship, a specialized cable-laying vessel. These things are floating engineering labs. They've got massive tanks below deck that hold hundreds of miles of cable, coiled up like the world's heaviest spaghetti. They've got robotic arms, underwater vehicles, positioning systems accurate to within a few feet, and they move slow, like really slow. When you're actually laying cable in deep water, the ship moves at walking speed, maybe 4 or 5 miles per hour. Because you're not just dropping cable, you're lowering it carefully, controlling the descent, making sure it lands on the seafloor exactly where you planned. In deep water, this is actually easier. The cable is relatively light down there, protected by water pressure from most threats. You just feed it off the back of the ship, let it sink, keep moving. But in shallow water, that's where things get complicated. In shallow water, you've got to bury the cable, because that's where ships anchor, where fishing trawlers drag nets, where underwater landslides happen, where sharks live and apparently think fiber optic cables look delicious. So you send down a remotely operated vehicle, basically an underwater robot equipped with a plow or a water jet system. This thing digs a trench in the seafloor, the cable gets laid into it, and then sediment covers it back up. You're essentially plowing a field at the bottom of the ocean while a ship slowly moves forward and a cable feeds down from above. The precision required is bonkers. And this process goes on for weeks, sometimes months. A single transatlantic cable project can take a year to complete from start to finish. Ships crossing back and forth, crews working around the clock, engineers monitoring every foot of cable as it goes down. Now here's what makes this even crazier. While you're laying this cable, you're also installing those repeaters I mentioned. Every 50 miles, you've got to splice in an amplifier station. These things are built into the cable permanently. They're sealed units about the size of a small refrigerator, and once they're down there, they need to work for 30 years without maintenance. Think about that. You're installing electronics at the bottom of the ocean in complete darkness, under crushing pressure, and they need to work perfectly for 3 decades. No software updates, no repairs. Just continuous operation, amplifying light signals powered by that copper tube running through the center of the cable. And somehow this works. There are more than 500 submarine cables currently operating on the ocean floor. They connect every continent except Antarctica. The total length of all these cables combined is over 800,000 miles. That's enough to wrap around the Earth 32 times. But here's the thing nobody warns you about. These cables aren't invincible. They break all the time. So let's talk about what actually threatens these things. Because it's not what you'd expect. Sharks are real. I wasn't joking about that. Sharks, for reasons scientists don't fully understand, sometimes bite submarine cables. Maybe it's the electromagnetic field from the power running through them. Maybe it's vibrations. Maybe sharks are just curious and their way of investigating things is biting them. We don't really know. What we do know is that it happens enough that cable manufacturers started wrapping cables in Kevlar-like materials specifically to protect against shark bites. Google even released a video a few years back showing their cables with special shark-resistant coating. This is a real engineering problem that required a real solution. But sharks aren't the biggest threat. Not even close. The biggest threat is fishing trawlers, ships dragging nets or anchors across the ocean floor. They snag cables constantly, especially in shallow waters near coastlines where fishing activity is heavy. A trawler drags an anchor, it catches on a cable, and suddenly you've got a broken connection between two continents. Then there are earthquakes. Underwater earthquakes trigger landslides. Massive amounts of sediment sliding down underwater slopes, burying or severing cables. In 2006, an earthquake off the coast of Taiwan triggered underwater landslides that cut 8 different cables. Internet and phone service across Asia basically stopped. Millions of people offline. International businesses paralyzed. All because the seafloor moved. Ship anchors are another problem. A cargo ship drops anchor in the wrong spot or drags anchor in a storm and boom, cable cut. This happens more often than you'd think, especially near major ports where ship traffic is intense. And here's the uncomfortable truth about all of this. When a cable breaks, and they do break, roughly 200 times per year globally, you have to fix it. At the bottom of the ocean, in the dark, sometimes in water that's 3 miles deep. So how do you fix a cable you can't see thousands of feet underwater that's probably buried under sediment? Here's the process, and it's genuinely wild. First, you have to find the break. The cable companies monitor their cables constantly, running diagnostics, watching for signal degradation. When a break happens, they can usually pinpoint it to within a few miles based on where the signal stopped. Then you send a ship, the same kind of cable-laying vessel that laid the cable in the first place. It heads to the location, and they start dragging grappling hooks along the ocean floor, trying to literally hook the broken cable and pull it up. Sometimes this takes days. You're fishing for a cable in pitch darkness, miles below the surface, in an area that might be dozens of square miles. Eventually, you snag it. You pull it up, and I mean pull it up from potentially 3 miles down, which takes hours, and you cut out the broken section. Then you splice in new cable. Right there on the ship, you've got clean rooms on these vessels where technicians carefully splice fiber optic strands back together, reseal everything, test the connection. Then you lower the whole thing back down, making sure you've got enough slack that the cable sits on the seafloor properly without tension. The entire process can take 2 weeks, sometimes longer, and it costs hundreds of thousands of dollars every single time. But here's what gets me. Despite all of this, the sharks, the earthquakes, the fishing trawlers, the insane complexity of repairs, these cables work better than satellites ever could. And that's the part that really challenges what everyone thinks they know. Because satellites sound futuristic, right? Wireless, space-based, high-tech. Cables sound old-fashioned, ancient, something from the telegraph era. But cables are faster, way faster. Here's why. When you send data via satellite, that signal has to travel from Earth up to a satellite in orbit that's about 22,000 miles up for communication satellites and then back down to Earth. That's a 44,000-mile round trip. And it happens at the speed of light, sure, but distance matters. That round trip creates something called latency, delay. When you're on a satellite internet connection, there's a noticeable lag between when you click something and when it responds. Maybe half a second. Doesn't sound like much, but for video calls, online gaming, financial trading, anything requiring real-time interaction, that lag is unacceptable. Submarine cables don't have that problem. The data travels through fiber optic glass at about 2/3 the speed of light in a vacuum, fast enough that the delay is measured in milliseconds. When you're video calling someone in London from New York, the data crosses the Atlantic through a cable in about 60 milliseconds. You don't even notice. Plus, cables have bandwidth that satellites can't touch. A single modern submarine cable can carry terabits of data per second, multiple terabits. You'd need hundreds of satellites to match the capacity of one cable. And satellites are expensive to launch, expensive to maintain, and they eventually fall out of orbit or break down. Cables just sit there, working for decades. But here's where the psychology gets interesting. Why do we think satellites run the internet when they clearly don't? It's because we can't see the cables. They're invisible to us, at the bottom of the ocean, completely out of sight. Satellites, on the other hand, we can see, well, kind of. We can imagine them up there. We've got this mental model of space technology and beaming signals and futuristic communication. Our brains love that story. It feels advanced. It feels like progress. It fits our narrative about technology getting more wireless and free and everywhere all the time. But the truth is literally the opposite. The internet is getting more physical, not less. Every year, companies lay more submarine cables, faster ones, higher capacity. Google, Facebook, Microsoft, Amazon, they're all investing billions in new cables because they know that's where the future actually is. And this is what nobody wants to admit. The internet isn't in the cloud. It's not wireless. It's not magic. It's infrastructure. Physical, tangible, vulnerable infrastructure that requires ships and engineers and constant maintenance. Let me show you what this looks like in practice. Let me tell you about two different ways people think about the internet and why one of them is completely disconnected from reality. Meet Jessica. Jessica's a graphic designer in Seattle. She works with clients all over the world. She uploads massive design files to clients in Germany, video calls with a team in Singapore, downloads stock photos from servers in Amsterdam, and in her mind, all of this happens wirelessly. She thinks of the internet as this omnipresent thing, like air. It's just there. When her internet goes down, she assumes it's her Wi-Fi, or maybe her internet provider. She never thinks about the fact that her connection to that client in Germany depends on a cable running across the entire Pacific, down around South America, or across the Atlantic, and up to Europe. She never considers that an earthquake in Taiwan or a fishing boat in the Mediterranean could cut her off from half her clients. So when there's an outage, like when those cables off Taiwan got cut in 2006, Jessica's completely blindsided. She doesn't understand why her internet is down when her Wi-Fi is working fine. She doesn't have a mental model for what's actually happening. The infrastructure is invisible to her, so when it fails, it feels random and inexplicable. Now compare that to Marcus. Marcus works in IT for a financial trading firm in New York. He understands exactly how data crosses oceans. He knows which cables his company's traffic runs through. He knows the latency between New York and London is around 60 milliseconds on good days. And if it spikes to 75 milliseconds, something's wrong with the cable. When Marcus hears about an earthquake off the coast of Japan, his first thought is about submarine cables. He checks the cable maps, he looks at which routes might be affected. He has backup plans for rerouting traffic through different cables if needed, so when an outage happens, Marcus isn't surprised. He anticipated it, he prepared for it. His understanding of the physical infrastructure means he can plan around its vulnerabilities. Notice the difference? Jessica thinks the internet is magic, so when it breaks, she's helpless. Marcus understands its infrastructure, so when it breaks, he's ready. And this isn't about Marcus being smarter. It's about having an accurate mental model of how things actually work. Here's what most people don't realize, and this is the part that changes everything. The internet isn't a technology problem. It's an infrastructure problem. And infrastructure is always physical, always vulnerable, always requiring maintenance and investment and planning. The people who succeed in understanding the internet, whether they're IT professionals, policymakers, business owners, or just regular users who want reliable service, don't think of it as this magical wireless cloud. They understand it as a physical network with specific routes, specific vulnerabilities, specific dependencies. It's not about being more tech savvy. It's about understanding that everything, even digital stuff, ultimately comes down to physical reality. Cables, ships, engineers, repairs. Once you see the internet this way, everything changes. You understand why certain countries invest billions in cable landing stations, why tech companies pay for their own private submarine cables, why international incidents involving ships or earthquakes can crash financial markets. You see the geopolitics of it, how cables route around countries that don't have stable relationships, how governments can tap cables for surveillance, how a country could theoretically be cut off from the internet entirely if all their cables got severed. You understand the business of it. Why internet service is more expensive in some countries than others, because they're farther from cable landing points. Why small island nations sometimes have terrible internet despite being surrounded by water, because no one's laid cables there yet. And you understand the fragility of it. How much of global communication depends on cables that sharks bite and fishing boats snag and earthquakes bury? This is the uncomfortable truth nobody wants to talk about. We've built this entire global communication system that feels instantaneous and magical and infinite. And underneath all of it, holding the whole thing together, are cables lying on the seafloor getting gnawed on by fish. So here's what we've uncovered. The internet isn't what we think it is. It's not satellites, it's not the cloud, it's not wireless. It's hundreds of thousands of miles of cable stretched across the ocean floor, connecting continents, carrying 99% of international data. These cables are engineering marvels. Fiber-optic strands, thinner than hair, wrapped in layers of protection, laid across underwater mountains and trenches by ships moving at walking speed. They work for decades with no maintenance, amplifying signals every 50 miles through repeaters that sit in crushing darkness at the bottom of the sea. And they're vulnerable. Sharks bite them, fishing boats snag them, earthquakes bury them. Fixing them requires ships and grappling hooks and weeks of work. But they still work better than satellites ever could, faster, higher capacity, more reliable. The question isn't whether you can have magical wireless internet that just exists everywhere. The question is whether you'll recognize the physical infrastructure that makes it work when it shows up in the news. Because now you know the internet isn't magic, it's engineering. And engineering requires ships and cables and people willing to fix broken glass at the bottom of the ocean. So next time your internet goes down, you won't just assume it's your router. You'll wonder if somewhere 3 miles underwater, a cable just snapped. You'll think about the ship that's heading there right now to drag grappling hooks across the seafloor trying to find it. Because once you see the internet as infrastructure instead of magic, you can't unsee it. And that changes how you think about everything from your Netflix binge to global communication to what it actually means when someone says their data is in the cloud. It's not in the cloud. It's at the bottom of the ocean. And it's been there the whole time.